Hi, and most welcome to Tech Tuesday with SeaTwirl. We are really pleased and happy to see that so many of you have logged in today, that you are here. We had, of course, hoped to see you here locally, but because of the COVID situation, we are doing it online. So we will do our best to keep your interest and send out energy to you out there. My colleagues at the company, Jonas Boström and Andreas Börjesson, will help me today to present the company. We will talk about the technology behind our innovation and products, and also take a little bit of a peek into the future. We are doing something at SeaTwirl that we really are excited about, and we want to share with you. We've been waiting for this day for some time, and now finally we have the chance to go through our work and our products. SeaTwirl is a development and innovation company that has been around since 2012. As I said, the company is built around an innovation on how you efficiently extract energy using floating wind turbines. We are listed on the Nasdaq First North, and if you want to visit us, and I hope you will in the future, you will find us at Lilla Bommen in central Gothenburg. Our business idea is to develop, produce, and sell offshore wind turbines. So we want to be involved in the complete process from the idea to the finished product. We had a very long time, we have a very long horizon. So we are in it for the long game. We want to build, and we are building, a competence center around offshore here in Gothenburg. And that's why we proudly want to present our team during the presentation, and also what we are doing. We even have experts that has moved from America, from Spain, from Germany, to join our forces here in Gothenburg, and we are very proud of that. We also, of course, work with subcontractors and other experts in the areas where we need some extra expertise. And our vision is to become a global leader within floating offshore wind power. It's a very ambitious vision, but we feel we have something great going, and we are very confident. So a good gut feeling. The mission, we all want to actively contribute to limit the global warming. And I think we all feel very excited about working with renewable energy. That is a privilege. And we want to develop floating turbines where the offshore environment is the starting point. We want to take something and build something for the ocean from the start, not something that you have produced that works well on land and then try to simulate land at the ocean. We also want to deliver the lowest LCOE, and that is the levelized cost of energy. It's a measurement used to compare alternative methods of energy production. So you put the energy production in relationship to all your costs. That means that you have to have check on your production cost, your installation cost, your service and maintenance, but also decommissioning of the unit. So it's the whole lifespan of cost. So that's where we are. We also want to build, I talked about it before, a competence center in Gothenburg. We want to be involved, and we want to be involved from the start to the finish. Another thing that is really our mission is to develop solutions to lower the cost for offshore wind power. To be really competitive and to be the selected and the preferred energy source for the future, you need to produce very efficient numbers for the LCOE. A few words about the market trends and also what driving forces in our markets. The climate change is one of the greatest challenges of our time, and I think we all can feel and relate to that. We have a signed Paris Agreement where we have agreed to reduce the greenhouse gas emissions by 40% to 2030. And luckily, EU, including Great Britain, has taken the lead in this journey. So a lot of activities and a lot of exciting developments are done in Europe in the offshore wind arena. Oil and gas companies are also looking into broadening their offerings. So they are looking around for their future offerings. We have an energy that is increasing all the time. And according to Bloomberg, the report, they estimate that the energy increase will increase by more than 60% by 2050, which is a lot. And in Europe, the renewable energy is forecasted to be 80 to 90% of that, which is quite a lot. And then globally, 2050, you talk about that sun and wind will be half of the energy that is consumed. So oil and coal are the ones that are decreasing, and sun and wind are the increasing energy sources. So we are in the right area. Okay, so why offshore wind power? Well, first of all, the ocean covers 71% of our globe. And there is so much energy in the wind out at sea. The wind is much stronger. The wind blows more hours per day. And the wind is less turbulent, which is very important. When you think about a wind turbine operating for 25 to 30 years. This extra energy is so important and is something that we all want to use for future technology. It's also so that wind energy has a cubic relationship to the wind speed. So if the speed is increased by 2, the energy increases by 8 times. So very important factor again. And now we come into something we call capacity factor. And capacity factor is a figure used to compare the actual production over a time to its maximum production. So at land, you typically have capacity factors about 30%. And offshore wind, it's going to be around 50 or more. And again, 25 years of production, that is a huge difference. Locally produced energy. Well, this is something that is also really important. With offshore wind, we can produce near cities and population centers because they are usually located very near the ocean, near the water, and also it's where the energy is increasing most fast. There's no place to build on land because we are expanding, and it's also become controversial among local residents that they feel that the turbines are destroying the local environment. It's not beautiful to look at. We can solve that by producing the energy out at the ocean. And we also have another great effect by this. Since we are floating offshore wind, we can adjust to the bird, what is it called in English? Fågelstråk, bird, where the birds fly. So we can move around. We can also look into where the transportation for ferries and other industries are working. So we are much more flexible. A few words before we go into our solutions. I want to talk about Europe again. There's a lot of interesting activities going on, and most of the times our competitors has taken an horizontal solution, and you will know much more about horizontal versus vertical when Jonas and Andreas are done with their presentations. But most of the times they have taken a solution that works on land and placed it on something that simulates land at the ocean, which is very complicated. And as you can see on the picture here, we have the first to the left is Principal Power, which is an American company, and they have an installation in Portugal. We have the French Ideol in the middle, and they have like a damping pool to stabilize their structure. And to the right, it's to the right for you guys as well, you have the high wind Equinor, which is SeaTwirl. And they have installations in Norway and Scotland, and looking into future installations. And as you can see, and we'll know more about in the coming presentations, they are using the same flotation substructure as we are doing, which is called a spar. So I'm really excited that we can tell the big difference between our innovation and the competitors. We have something unique, something built for the ocean from the start, and I think that's going to make a huge difference in the future. And you will get to know us and our technology much more when Jonas comes on stage. And I will come back in the end and talk about, when you learned much about our technology, I will say a few words about where we are going, what is the potential markets, and if we could dream, what would we build? So thank you for me now, and I'll go into the next presentation. Welcome, Jonas.
Let's see if I can unmute myself. Okay, I managed that. Thank you, Peter. Splendid introduction. And now it's time for technical presentation part 1. So basically, I will wish you all welcome to Tech Tuesday, and I will go into more to technology. They have let the engineers on the stage, and we shift the focus to the technology. I am Jonas Bostrom, CTO of this company, and been here since the end of 2017. I will be joined by Andreas Börjesson, who been in the company since design of SeaTwirl S1. I must say that we've been looking forward to presenting the technology, both me and the team, for some time now, and we are very happy to have this opportunity. The first part of the technical presentation gives you the basis for the second part after the break. I will go through the general concept, mentioning some words about our patents and strategy around it. And Andreas will go through some of our benefits and learnings from S1. We would appreciate questions and have dedicated 10 minutes after this section and additional 15 minutes after next session for just that. So, due to the circumstances, please send in your questions during the presentation, and I will read them and answer them in the end of each session. So you have the email address here. I will linger a little bit on this slide, info@seatwirl.com. Please, shoot away. Before getting into the actual presentation, I would like to give a big thumbs up for the team. You will hear me and Andreas present the technology today, but we would have nothing to present if it wasn't for the great team. The technology department consists of 8 full-time employees, all of which have high level of competence and the highest level of engagement. We are all working for something that we really believe in and are here to make a difference. This is a short statement. This short statement is something that shines through the everyday work and the achievements so far. I am impressed of what we have accomplished with the resources that we have used so far. Okay. A presentation of the general concept utilizing SeaTwirl S2. That is the project with most focus at the moment, a 1 megawatt floating turbine. But we need to get some terminology out of the way, and then I will go through the general principle of to get everybody up to the same level, basically. The heart of the SeaTwirl concept is the vertical axis wind turbine with a tower connected to the spar, with a fixed ballast in the bottom to increase stability, just like a keel on a sailboat. The turbine and the underwater part is rotating as one, while the generator housing is moored to the seabed to keep the rotational unit in position, both in translation and from rotating. Between the rotating parts and the generator housing, there is a bearing. Using the fact that the whole structure unit is floating in water, we can simplify the bearing arrangement to mainly carrying the radial load, and the actual load is carried by the water. This also makes the bearing relieved from any kind of overturning moment. I will linger upon the concept that the turbine and the spar is rotating. This video will illustrate just that. And it takes a few seconds to get your head around it, but I have shown this video several times, and after seeing this, many are on board. So I think it's going to be crystal clear after seeing this illustration, at least. So you can see that the turbine is rotating and the spar buoy underneath is rotating at the same very speed. Okay, so the heart of the SeaTwirl concept is the vertical axis wind turbine, and therefore some fundamentals of a vertical axis wind turbine is in place. In the second session we will dive more into the details of how we have simulated this, and but this is the basis. There are a lot of arrows, but bear with me and I'll take you through it. Here we see the turbine from above. The wind is inbound from the top of the and the azimuth position is defined at 0 in the rotor blade position to your right. See if this one works. It does. Fantastic. So how is this kind of a turbine generating torque? The blades have wing profile that for certain wind speed and angle creates drag and lift, just as on an airplane. Here we rotate, thus the apparent wind, the black arrows outside the air will change and during the rotation. The blades generate lift, and when the lift is higher than the drag, then you have created torque. Basically the lift is the green arrow, the drag is the black arrow, and it's an easy example here. You have 0 lift when you are deadhead to the wind and when you're following the wind. So the torque generated from the each blade is shown in the graph on the right for you as well. Yes. The highest lift force is closest to the wind, and that's where you extract most energy. So congratulations. Basically you have now examined the basic course of that knowledge. Let's move on. We zoom out again. Look at overall concepts some more. We're mentioning that the keel effect and that it's relieving the overturning moment from the bearing. This deserves a little bit more attention. And we have made a short movie about that as well. So as the wind force, here we can actually start from the gravitation from the keel is countered by the flotation of the body. Then you have the wind force pushing the turbine to start heeling. As we are heeling, the flotation and the gravitation is offset, creating a moment, and this is countered the moment from the wind and the mooring. We should have arrows coming up illustrating just that in a second. So basically, and here we see wind, but it's not only wind that works on it's also waves and currents. So there you have the arrows. Basically the wind tries to heel it over while the keel keeps it in place. There we go. So if the vertical axis wind turbine is the heart of the concept, the generator housing is certainly the brain. This is a teaser for the presentation after the break, but it's well worth planting a seed. We have achieved to move all the maintenance heavy components to easy access area close enough to the water surface. In the generator housing, the torque from the rotational tower and spar is converted to electricity and exported to shore via the export cable. It is two generators that are engaged in the drive main gear via the gearbox. Two independent brake system, power electrics, support frame, boat landing, and gantry for maintenance. So these systems some of these systems will be discussed in the next session, but not all of them. And then we have the pre-tension mooring coming into 3 attachment points on the generator housing and connected to three lines. And in the center are the tower, and the spar is rotating in a protected area. Well, here I'm focusing on the advantages of a spar buoy. There are of course disadvantages as well, where the most known is installation. Basically it is hard to handle the long slender structure in shallow waters. The spar does however provide benefits that overweights this. Some points here. To start with, the spar is the only floating structure that can rotate in water without significant losses due to low rotational speed. That the whole spar rotates enable the bearing solution I will be speaking about to not take the overturning moment created from the wind speed. Everything is placed in an easy access area. This is not only the bearing of course, but it's also all the components that we have in the easy access, easy to get close to the spar. The spar design is cheaper than a semi-submersible structure. Tubular structure is one of the easiest controllable steel structure there is. Our spar is only stiffened by ring stiffeners and bulkheads that ensure water integrity. All in all, simple, robust and cost-efficient design. Okay. Patents. Patents are important. A strong patent portfolio, that's what we have. SeaTwirl have since the start put a lot of focus on protecting our basic technology. So far we have had a good track record of filing and getting patents with grants where we find the terms are very generous. This is very important and it gives us good and wide protection. We are continuously growing our patent portfolio. Let us take a look at some of the patent families we have. So let's start with the uppermost, the offshore energy storage device. Flywheel arrangement that utilize liquid moving between the flywheel and the center part, which provides either changing in rotational speed or storage of energy. Imagine a big park of SeaTwirls. We can harvest we can act as a battery for the energy system or the grid. Dynamic turbine system. The wind turbine is foldable by pivot the blades. The application for turbine in hurricane areas typically. It is to decrease the loads on the turbine. And then I think the most important one actually is floating wind energy harvest apparatus with replaceable energy converter. This started out as an exchange method for the generator housing, basically take the full generator housing and exchange it. But in the filing process we basically have in the claims that we have that we can do a vertical axis wind turbine that is mounted with 3 different pieces. And it's quite hard to do a vertical axis wind turbine without having three bodies connected with, for example, bolts. Some more. The one to your left is have been achieving PMs quite recently in different countries. It's a braking arrangement that's reducing the speed for the turbine, utilizing the close-by water, basically elevating the water from the water surface. Here we have, and then the 2 second ones are quite new, filed this year. Mooring tensioning procedure, a method of doing the pre-tension of our floater. And then we have a blade to strut connection, a cost-effective way to keep the strut and blade connected to each other. With that basic crash course in SeaTwirl concept that I've given you, I will leave the word over to Andreas and hope you enjoy him for the next coming minutes. He's going to be talking about the learnings from S2 and our benefits.
Thank you, Jonas. Hi everyone, I'm Andreas. I've been on SeaTwirl since 2014. I will go through some technical advantages of the SeaTwirl system. Advantages of vertical axis wind turbines really come to play when using the technology offshore in a floating solution. A vertical axis wind turbine is independent of the wind direction. So the SeaTwirl turbine rotate around a vertical axis and it will always have one part of the turbine facing the wind. Whilst horizontal axis wind turbine need a mechanism, it need a yaw mechanism to turn the turbine towards the wind. In addition to that, SeaTwirl have fixed blades on the turbine, keeping the structure simple and robust. This results in SeaTwirl having fewer moving parts. As Peter mentioned earlier, there are a large amount of energy available offshore, but the weather conditions offshore also limit the availability to go to the wind turbine. And sometimes you must await a certain weather window to be able to go there and perform operations on the wind turbine. It is therefore important to have a reliable and robust technical solution to minimize the downtime of energy production. And SeaTwirl argue to have a good technical solution with few moving parts that can break, and thereby minimizing the downtime, maximizing the time for production. The green marked areas indicate where the generators and the bearings are placed. This is heavy equipment. The SeaTwirl concept allows for a low placement of heavy equipment, and therefore SeaTwirl have a low center of gravity. And why is that important? Well, imagine yourself paddling a canoe and you try to stand up. When you stand up, you rise the center of gravity. You will feel immediately the loss of stability. So low center of gravity is crucial for a floating structure. And comparing a structure with a low center of gravity to a structure with a high center of gravity, the SeaTwirl floater can be relatively smaller. This implies lower cost to manufacture. And having the generator housing placed close to the water surface also gives you easy access for service and maintenance operations. And there is no need for expensive offshore heavy lift cranes to perform these operations. SeaTwirl can have compact wind farms. Studies indicate that it takes a shorter distance for the wind to recover behind a vertical axis wind turbine than for a horizontal axis wind turbine. So therefore, SeaTwirl turbines can be placed closer together. And having more turbines at a certain area is an advantage. And this advantage also applies to the mooring system of a wind farm, since several wind turbines are linked together, and then they have a common mooring system going down to the seabed. A unique feature of the SeaTwirl concept is its powerful inertia, and that lets our turbine store rotational energy. SeaTwirl have a larger moment of inertia than horizontal axis wind turbines due to the placement of the blades. And grid stabilization will become more important when transitioning into renewable energy and weather-dependent energy sources. And having this large inertia gives a stable power production to the electrical grid and also low flickering. A higher inertia also results in a better ability to handle variations in wind speeds. These things together may become a possible economical advantage. The SeaTwirl design makes it possible to think big, as the vertical axis wind turbine has great potential for scalability. Different research studies conclude that the future vertical axis wind turbines could become as large as 30 megawatt. That is far beyond what are thought to be able to deliver from horizontal axis wind turbines. All of these advantages sum up to a lower LCOE. And to summarize, it is very important to have a reliable and robust technical solution when operating offshore, to have as many operating hours as possible. SeaTwirl have a solution with few moving parts, few parts that can break, which implies low downtime. SeaTwirl have a low center of gravity, and this is an advantage on stability and that the floater can be relatively smaller. And it also leads to that we have easy access for heavy equipment. The inertia of the system gives advantages to the electrical grid, and it's possible to have compact wind farms with SeaTwirl turbines. All in all, leading to a low LCOE. In 2015, we launched a prototype that we call the S1 in Lysekil. It's a 30 kilowatt turbine, and it's placed at the west coast of Sweden. We will look at a movie and some pictures from operating and during manufacturing, assembling, and installation. So here you see the S1. It's a 30 kilowatt wind turbine with 3 generators. It reaches 13 meters above water level and 18 meters below. It has 11 meter long blades, and the diameter of the turbine is 10 meters. The water depth at this current site is about 30 meters, and it has a sea cable of 250 meters. Most of the parts were designed by us and manufactured and assembled in Lysekil and in Gothenburg. Here you can see the spar buoy when it's manufactured locally in Lysekil. Here we have the main shaft inside the generator housing. You see the main gear connected to the main shaft as a part of our drivetrain. The brake disc for emergency braking and also statically locking the rotor when it's parked. Here you see the interface between the generator and the main shaft, which is between a pinion and a gear. All parts of the mechanical drivetrain are placed inside this generator housing, whilst the electrical inverter and transformer station are placed on land, and from there it's connected to the electrical grid. Here you can see anchors and buoys used for the mooring system. Here is pictures of our spar buoy. To the left you see the floating element of the spar, And in the middle you see when the floating element is connected to the keel. And to the right you see when the full spar buoy is lifted into the water via a crane. Here you can see mounting of the wind turbine and its tower onto the generator housing, and then when it is lifted onto the spar buoy already in water. Here's a picture of towing out of the full structure. And this is how SeaTwirl S1 looks. The design, manufacturing, assembly and installation was performed by a small SeaTwirl team together with suppliers. This indicates a simple technical solution. Designing, launching and running the SeaTwirl S1 have given confirmation on several technical systems that will look similar in the S2 unit. Those systems are the drivetrain solution, the braking solution, the stability of the structure, and also the mooring system and bearing solution philosophy. Now we are setting up for questions and answer round. We will answer questions shortly.
Do you see me? I think you see me. Hello again. Welcome back to Technical Presentation Part 2. First of all, I would like to say that we have received a lot of questions. Sorry for just taking 6 questions before. It takes a little bit to get them through the email and then up to us here on stage. I will have my presentation that takes about 45 minutes. After that, we will have a technical question and answer, and then Peter will come online again, and then he will have his presentation, and then we continue with the question as far as we can. We are a little bit ahead of schedule, so I hope that we can answer many questions for you. So I hope that I don't leave anyone disappointed from the first session. Let's remind everybody though, please keep on sending in the questions to info@seatwirl.com. This is very fun and very useful for us. Thank you very much. I will present now, and then it's 50 minutes. Okay, and this is all because of the current situation. We would like to have you all here, of course, but I would read up the question and then answer them as I did before. Okay, in the previous session we have talked and taken you through the concept and the benefits with it. In part 2 we take a step further. The focus is on the technology here, and more precisely the technology development of SeaTwirl S2. The goal with today's presentation is to give you more insight in the work behind the design. We design floating wind turbines where the turbine is integrated in the floater, which is quite unique. We will try to split the system up into different parts, and I will take you through the full system today, from mooring and floater to power system and turbine. So the agenda will be time plan, simulation methods, control and safety system, turbine, generator housing and electric system, the spar and mooring, and then I'm finishing off with some words about S2 and the pilot site we're going to use. All right. It's always hard to limit the scope in a presentation like this. We would like to take deeper into all the technical challenges, but that means, we can't basically. So we have limits our part here to simulation and design. And but I will mention some parts about manufacturing and long lead items during the presentation. But I mean, there is a lot of things that we have done more than just presented today. Time plan. We are now in 2020, and it is 1.5 years left to the launch of S2 in 2022. We have an emission coming up, and the money raised for this from this enables us to make commitments and activate procurement. For many of the long lead time items, we have already formed collaborations. with the supplier, with documentation in place for a push of the button order. We have an exciting time ahead of us, and we are very much looking forward to see S2 in the water 2020. And we're not alone. There are many people that would like to see this in the water 2022. The work is not over with S2 installed and commissioned. It's a process afterwards. Evaluating the S2 is a big step of this, and making it in order to make it a commercial success. The focus today, from my part, is on S2, but there are other projects existing, and I think Peter will mention some in the end. Okay, quick recap. We are now digging in deeper to SeaTwirl S2. I will not show the rotational movie again. Everybody knows that, and but rather say that the heart of the concept is vertical axis and bring forth some terminology. If you remember the agenda, some of the terms are familiar. From the top to the bottom, the blades, strut, tower, forms the turbine. The generator housing is our term for a nacelle. Here you find generators, brakes, gearboxes, electrical power system, and much more. The generator housing is kept stationary by the mooring, both in rotation and translation. The mooring system stretches all the way down to the seabed and is configuration for the specific site. The flotation is provided from the spar buoy and stability from the keel with the fixed ballast. There are several individual components that in itself demands a lot of development, and then the whole system that shall work in harmony. We have designed a floating wind turbine for offshore from the start to finish, and at the centerpiece of this is to utilize the right tools. Therefore, I feel it's a good start to start with the simulations and what we've done so far. So to achieve the design of the turbine and the spar structure, the load are essential. The complexity of the simulation is a trade-off from efficiency for time efficiency. The more that you include in the simulation, the longer it takes to simulate. SeaTwirl had an early opportunity of utilizing CFD for both blade and tower. These simulations have very high resolution, but they are time consuming. To have a run of a full simulation for 600 seconds is not feasible, but rather we use this as a first result for generic loads for our FEA. Furthermore, the result gave aerodynamic performance from a stiff structure, and these were derived to drag and lift coefficients that were put into a mooring analysis. Mooring analysis is a good tool to iterate design with low calculating cost for the whole system. Receiving accelerations, mooring loads, and sectional loads of the full structure make it possible to make a basic design of the spar, tower, generator housing, steel. The mooring simulation is also used in to set the design criteria for the export cable. To design the turbine, more load cases are needed to be simulated, and the actual environment needs to be more refined and incorporated in the model. This is done using a vortex method, which is an analytic way of capturing the stall of the blades that occurs 2 times for each duration of the rotation, just as we went through in part 1. I think I have a short slide of that repeating that. The stall is important to keep under control of it, since it has a large effect on the simulation. Here is an example of the torque when the turbine operates optimal, but for higher wind speed the turbine must decrease the efficiency and the blades, and then the curve changes. and the stall becomes even more important. First, the turbine was assumed to be fixed at the surface level, and the results were validated with CFD results. After validation, the turbine is assessed including aeroelasticity, the turbulent wind and wind profile. Aeroelasticity is that the blade is actually moving with the wind or deflecting during the simulation. The simulation runs for 600 seconds each, and the loads are extracted and inputted for FEA and design. To increase the accuracy of the simulations, with an aeroelastic solver. The last step gives a very good accuracy of how the structure will actually behave at site. The fully coupled solver is validated with the mooring. To speed up the process further and verify the design for more load cases, the actuator cylinder flow model is used instead of the vortex solver or vortex method for the bulk cases. Here everything is in a nice line. We're going from CFD to basically finished product. In the real world, it's a lot of iteration going backwards and forwards as well. But as an example, a natural leap after the simulation analysis is the control and safety system. We will limit ourselves to the turbine operation, but the safety system can, of course, be expanded to working environment, fire protection, maintenance procedures, and so on. And the control logic is developed by us, verified by subcontractors that have experience not only by floating offshore wind, but also with vertical axis wind turbines and tests of these. So I have great faith in these. The control system adjusts the rotational velocity and output power. This is done by increasing or decreasing the torque transfer to the generators, taking out less or more electricity, that is. The turbine is controlled by adjusting rotational speed to optimize the level of energy output while keeping the loads reasonable, meaning that high inertia loads are reduced, vibration avoided, and load variation minimized. In the best of words, everything can happen, but that is the importance of having SeaTwirl S2. So we can test this in real life and optimize the control system. Here we have a graph of how it typically operates and the power output from it. So what you can note here that you have 11 RPMs is basically the maximum speed of the turbine. If the turbine is rotating with 11 RPMs, you have a speed of the blades of about 30 meters per second. Add on the actual wind speed, and then you have a maximum air that hits the blade with 50 meters per second. Why is this important? The industry of wind power are struggling with erosion issues on large turbine blades, which is caused by a combination of high speed and particles and presence of particles. Reducing the speed reduces the energy of the particles hitting the leading edge with a square relation, and thus we will have less maintenance. The SeaTwirl S2 concept is stall regulated wind turbine, which has a rotational velocity control done by means of controlling the electrical torque from the generators for a given rotational speed. If and this torque to speed is known, so if this isn't matching, then the speed will be decreased or increased depending on what is most efficient, and this is what happens in the region 2 to 4 here. And then for the last part where we have a stall control, and we making the turbine less efficient to not take out too much power, it's a proportional integrated controller that is used. From a controller perspective, safety system is about slowing the turbine to a stop if anything triggers it. Examples of triggers: high vibration, storm, overpower, overspeed, or failure of critical systems. There are two independent braking systems, and the system fulfills the regulatory requirement for floating wind power. We have a closer look at them when we get to the generator housing. Okay, the vertical axis wind turbine, the heart of the SeaTwirl concept. I feel I say that a lot. The turbine consists of 3 blades, 6 struts, and a tower. In part 1 we had a crash course of the turbine, the aerodynamics, and now we will go into the simulation of and the design of it. The turbine is designed by SeaTwirl team, an in-house design with a team that brings expertise within loads, control, and structure. The most advanced know-how is in-house, while we're utilizing consultants for verification, drawings, and manufacturability inputs. We take the global loads from all the simulations, CFD, vortex, actuator, cylinder flow, down to local submodels to evaluating and optimizing the blade, connections, struts, and tower. We have chosen manufacturer. This was posted for some time ago. It is Elite Composite. The manufacturer's site is in Uddevalla, close to the harbor, which makes logistics much easier. Elite Composite provides us support with manufacturability and material testing. I would say that we are very happy with the Elite Composite, and it basically gives us all we need at the moment. So, and I put this figure of Minesto Kite here because they deliver the wings for their kite as well, as a reference. When designing the turbine of S2, we have focused on designing driving parameters. The design has been under development and iterated several times before the current design. There is always a wish for more, and today's design may not be optimal in every environment, but it is robust design, fit for its purpose, yeah. The natural offloading for vertical axis wind turbines is that it has 2 stalled cycles for each blade and each rotations. This means that there will be a load variation, and hence the fatigue is of great importance. The figure at the right is an example of an in-house developed software, actually, evaluating just this. Eigenvalues, existing references indicating previous large vertical axis wind turbines have had issues with fatigue induced by low eigen frequencies. But ultimately, I mean, the fatigue and designing something for structural is always interesting, but ultimately it comes down to the costs. We are measured with the LCOE, and coming down with costs means basically everything. So there's a high focus on this, which makes it easy to do the traditional choice of steel tower and cast hub. Since they are cost effective and well-proven design, much can be taken from the already existing wind power industry, and it should be utilized. Then we have the blaze and strut that is almost out of 100% carbon fiber. So why carbon fiber? Specific stiffness of glass fiber is lower compared to carbon. Decision to go for carbon is to minimize the risk of eigenfrequencies issue in the prototype stage. In terms of cost, increase of costs of material, carbon is more expensive than glass, is somewhat offset by the decrease of material put into the mold, especially in a high-cost country like Sweden. The increased confidence achieved by using carbon thus is justified. Furthermore, an advantage are increased build quality as more qualified builder can be used, and oddly enough, it is also an environmental benefit. Carbon can be recycled. It's actually worth time to extract the fibers from the blades and strut and reuse the fibers for later purposes, and this kind of industry is already in place due to the airplane and the car industry. So the after we are done with the S2, it is fully recyclable when it comes to blade and struts. So we have done extensive FEA modeling. I will not show everything, but we have performed on all composites and steel material. Here is a sub-model of the blade and struts, where you can see the stack-ups defined in the on the boat struts and in these fields. And I actually put in a short list just to have it is a lot of work with these stack-ups. So only for one of these sections you have the full table there. And the green part you saw there was steel. More example, you have a submodel of the hub, and then you have a load, ultimate load for the blade on the tower with reaction forces. You have an evaluation of the tower with regards to deflection and stresses, and then an eigen frequency analyzer in the far in the down right corner. In-house design, local models for joint between blade and strut. You can see the this is actually the thicknesses of the layup, and then you have the detail mesh for the strut to blade connection. We have the capacity to run the full analysis within SeaTwirl. This is a key to ensure that extensive load runs are in line with expectations and correct. It is also enhancing the possibility to further develop the concept for the coming products, since we can do this full analysis in-house. The evaluation and verification of fatigue is one of the design drivers, where an in-house software extension enables us to create new functionalities such as specific load, failure criteria, post-processing steps, and custom results. Basically, it's a time saver when you're evaluating fatigue, and this has been possible to do due to the width and the competence of the team. I put the button here just to show that we actually have that in the software, and it's quite nice, I think. So this is how it looks like. I mean, it's not much for the word, but it's a big thing. In a fully coupled analysis, the structure of the blade and struts are divided into section and beams elements. It's the loads can be transferred from this model into a more refined shell model, and this then we can make the structure more efficient. The figure shows application of extreme loads from just one of those simulations. And after specific inputs, fatigue results from all the elements, and the specific geometry will be calculated and shown in colors, as in the figure here. So even I can follow. During the calculations, the Markov matrix and are generated and fatigue damage are evaluated in accordance to DVGL standards. This gives us high resolution results for composite and steel structure with minimum work. To validate the method, we have used we have verified it by use of the beam models from known from incorporated in industry acknowledged software. This brings us to the generator housing. Generator housing house equipment for transforming the rotational energy of the wind turbine into electricity. Only stationary part of the floating wind turbine. This is the only one. By having the generator housing placed close to seabed level, we get easy access for service and maintenance and low center of gravity. That's why it is where it is. This is the design is constantly developing, and it is always nice to see what a graphic artist can do. I like this one. In the coming slides, we have used CAD models and analyzing results, where the effort have been limited on the graphics. This is an illustration made where when we were evaluating if we could pattern R-sling solution. So it will be a slight difference in the connection points in the slides, coming slides, and you have already seen a couple of them. The generator housing is basically the home for all system and components. This gives us much to talk about, and we have tried to pick the ones that are most important. The main bearing solution, load distribution over it, the mechanical drivetrain, and power electrics, and the braking system. So the essential. So this is the view from a designer, and we have basically all that we will talk about. You have the bearing in the center, the structure that distributes the mooring loads from the mooring attachment points into the bearing. It's the transparent part here, and then you have for each, for the mechanical, we take a zoom in, I think. The generators are the purple boxes here. And there. The blue boxes are the gearbox. One on the incoming shaft of the gearbox, the secondary braking system is mounted. The generators, gearbox, and secondary brake system are supported by the frames, which is mounted in the interface of the bearing to distribute to not disturb the load distribution over the bearing. The interface which to the main gear is through a pinion within an enclosed gear guard, which enables controlled lubrication of the main gear system. The main gear is close to the main bearing to reduce the relative deflection as far as possible. The grey boxes that you see is the electrical power system that transfer the energy from the generators to the export cable. And for reference, a small iMic in the downward right. Alright, the main bearing. It's a large bearing. Here we see a section to the left. It is a triple row roller bearing. As the bearing is only providing rolling element, it is the structure it is seated in that provides the load distribution. Extensive investigation have been made to ensure that even for the worst load cases, we are well in the safe working area for the bearing. Here you see some examples of just that, having the mooring lines attachments and then how the load is distributed via the collars into the bearing. The bearing position together with the with the chosen mooring system implies mostly radial loads from the mooring onto the bearing. The loads from the mooring system is distributed from the mooring attachment point through the generator housing to the bearing. The generator housing is designed to distribute the load to a large part of the bearing circumference to utilize the full bearing. The bearing is perfect for this application. It is scalable and it is adaptable to our needs. A key in the development of have been a good collaboration with IMO, our bearing manufacturer, which have been able to verify calculation and propose innovative solutions for just this. We will go further into the drivetrain, but come back to the integration of the bearing. The power of the wind turbine is extracted from the main shaft via two generators. Via shaft. The two generator sets are placed on opposite side of the main shaft to get symmetric loading. The symmetric placement and symmetric placement of masses. They are mounted on a frame, which are isolated from the structure, distributing mooring loads and the bearing. Let us take a closer look. Okay. On the left you see the one generator set and the main gear with the gear guard on. I have zoomed in up here and taken away the gear guard to have a closer look at the interaction between the pinion and the main gear. The frame is mounted on the bearing support flange that can be seen in the lower figure right here. It is somewhat hard to see, and we will have a closer look at that as well. This section of view is made right in the center of the pinion. I will not go into every detail, but rather say that we have managed to make the interface of the mooring, transmission and rotation come together in a neat package, which with the thought of manufacturability, maintenance and cost. And a small comment here is that it's always easy to see when it's done, but it's been a lot of iterations before you have this neat package. And a section view of the mooring. I want to point out the mooring enforcement on the sides as well, distributing the mooring loads into the structure. I could go on about how the interface between the main gear and the pinion, how the deflections works, and if we are within tolerances, and how we align the frame to the main gear, and how the eigenfrequencies and the structure, how it's behaving from the loads. But we need to move on. Okay, from having the wind turbine rotating in operation, there are three ways to slow the wind turbine down. So this is the braking system. The main way is by regenerative braking using the generators. This is a controlled acceleration and shutdown procedure that is performed within a minute from the rated power. This is also the preferred way to slow the turbine down. This is the normal way of slowing it down. But in case of fault or electrical blackout, we have two mutually independent braking systems to bring the wind turbine into a standstill. One, by applying the emergency brake. The emergency braking system consists of 4 brake calipers. You can see them. You can see 2 of them at least in the one down to the left. That works directly on a large braking disc mounted on the shaft, on the main shaft. The secondary braking system consists of two smaller brake discs acting on the generating gearbox shaft and thereby braking on the drivetrain components. To hold the wind turbine stationary during parked condition, a rotor lock is installed, locking the main shaft from rotating when it is in a standstill. In case of an electrical blackout or failure of the rotor lock, the emergency brake have enough static brake torque to hold the wind turbine locked during the roughest weather conditions for the wind turbine. The electrical system. Alright. The electrical system is basically the boxes you can see here, transforming the energy from the rotational turbine into electricity on the grid. It is somewhat difficult for me to make myself understood by pointing at these boxes, and so thus we'll have a look at other boxes basically. So here we go. The main goal for the wind turbine is to produce as much energy as possible for every given wind speed over a certain time. We have opted for a fully power converted system. What that essentially means is having power electrics between the generators and the grid to give full control of the voltage being produced until it delivered onto the grid. If you look at the pictures, the following is happening. Depending on the wind speed, a certain amount of power is transferred from the wind to the turbine. When the generators are engaged, they produce a three-phase voltage handled by the motor modules. This voltage is then rectified and directed to the active line connection. The active line connection module is essentially an advanced inverter that is feeling the grid and making sure that the phase and the frequency is matching the grids when it's transferred out to the transformer. The transformer transforms the voltage from 690 to 22 kilovolts, which is custom fit for the grid at site. Okay, mooring. So now we have mooring system, Sparboy, and then just the S2 site, and these parts are going quite quick actually. The mooring system. The mooring system's function is to restrain the rotation of the generator housing and keep the position within a certain displacement. We will now go into the configuration of the system, but please take a look at the buoys because they are not shown very well in the next slides. The function of the buoy is to relieve the spar from the weight of the mooring system, and also to and also relieve it from the increased downward pull that acts when the line is getting taut. So here is a setup of a simulation for a site-specific mooring system. It is way too much to have in a presentation actually, but it is to show that the complexity of it and how many and the number of variables that are available for the system. What you see in the sea is the seabed in brown lines and dots. The blue ones are water. The mooring lines going out from the floater turbine, and the export cable is the last one that is with a little bit thicker yellow in a lazy S configuration on the left hand side. There is a wide range of options, and we have limited the configuration to what is standard for offshore drilling units, since this is available on key both to buy and to rent, which is quite common for periods of 5 years or less. And I will focus on the setup and configuration of the mooring lines. What you see here is another simulation without the export cable. This is a more time efficient way to simulate. The figure is mainly chosen because it gave a rough overview of the delta sling, and a very rough one. This is probably the only exotic thing with the mooring system of S2. The rest is pretty much standard components, and there are a lot of consultancy firms that would be able to do the design and analysis of the mooring system. What is unique for S2 is the torque restriction requirement. That is why the mooring lines are split close to the generator housing to ensure that the system always is taut. I thought we can revisit these figures, and I can mention some words about the red arrows in this graph that I didn't mention anything about. It is to take the torque. The lever arm times the difference equal the torque. So basically this is design, so the lines will never go slack in the pre-tensioned mooring system. Clarify that. You have a tension here, and then that load is distributed on the two lines. When you're getting torque, then more load will be taken by one line to compensate, and the torque will be what's created. Other than that, we have a mixture of standard components, 2 steel wires going out to the tri-plate, that's the delta sling, polyester ropes to the buoy, and from the buoy to the bottom chain connector. We also have polyester and then we have chain to the anchor. So basically the red ones are polyester, and then chain is the yellow ones. And here it is a basic list. The short result is that the system consists of 3 lines with a minimum braking load of 5,800 kilonewtons, will sustain all possible load cases in accordance with the rules and regulations. I also include the buoy, which are about 6 meters tall, so it's quite substantial buoy, which reduces the downward pull from the mooring and the weights of the mooring. I will not dwell more on the mooring system actually, I will leave it at this, and then looking forward to comments and questions there. So the spar buoy, let's move on to the final structure member, the spar buoy. In part 1 we mentioned the benefits and why we have chosen the spar buoy as a floater, and here we will touch upon the technical part of it. Well, basically, if I was to keep this very short, I would say the spar is designed and dimensioned according to DVGL rules and guidelines. It provides flotation and stability. We can make it a little bit more. Anyhow, I will press on that the spar is designed out of tubular sections, only stiffened by ring stiffeners. We can take a more mentioning picture out of it here, and bulkheads that ensures water integrity. All in all, sheep manufacturing is that is well under control, hence robust. In total, the spar is equipped with 3 ballast tanks, 2 that is filled with water, and 1 that is fixed. One fixed ballast located at the keel. The 2 water ballasts, they act as adjustment when during installation, and adjusting the draft to being exactly where we want it to be. And they are of course placed as far down as possible to lower the center of gravity. The flotation is provided from the enclosed area above the tanks. So basically all things that is above the 2 water tanks that are our flotational part, and the lower section and below the water tanks it is open to the sea, So basically this, the lower part is also filled with water and has the same pressure as the ocean outside of it. The surface of the spa is smooth without protruding parts in order to keep the friction low and hence also the losses as low as possible. This is also the reason for the geometric shape, where the lower section of the spa have a smaller diameter than the upper part, reducing the velocity of the spa surface and the surrounding water, towards the surrounding water. All right. Oh, here the actual ballast are indicated. So let's have some words about the funny-looking shape on the bottom. The spa's advantage is that it has a small motion magnitude in vertical plane due to the small vertical plane area. However, resonance may occur for long wave periods, and to reduce this heave motion and avoid the resonance, a heave plate have been added to the spar hull. This change the hydrodynamics properties by adding extra dampening. That's the blue arrows in the graph here. In case of S2, it is also filled a secondary purpose, which is to fill the ballast tank with fixed ballast and getting everything at a low position. And this, the drag coefficient is calculated through the CFD and then incorporated into the mooring analysis. The spar design is driven by fatigue load, installation loads and frictions. The design work has been carried out using analyses that ensure that not only the flotation stability of the spar is verified, but also structural integrity through the life cycle of the spar. So here you see an example of installation maneuver and then how the flotation device in an upstanding area, and then you have the structural integrity on the right. Finally, I have 2 slides left. The SeaTwirl pilot installation site is situated at the west coast of Norway. The water depth of the installation is approximately 100 meters. The site offers possibility for connection to the power grid. The connection point is positioned on shore, approximately 1 kilometers from the planned installation site. Further, the site has good communication between Haugesund and Stavanger. Basically, there will be a lot of traffic going past it, and we will see S2, so the public will see it, and it's very good. The final assembly of S2 unit will take place on the west coast of Norway, close to the installation site. Once fully assembled and all preparation have been made, the installation at site may commence. The fully assembled generator housing and the turbine is mated with the spar at either the pilot installation site or in close vicinity and towed to the installation site. Different installation sites have different challenges and conditions. Further, the number of turbines to be installed will also have an impact on the most cost-effective installation procedure. Hence, SeaTwirl are currently working on several installation methods to ensure robust and cost-efficient installation method sustainable for everything from case by case to large-scale installation of numerous wind turbines. SeaTwirl are working with several external partners for analysis and development of the different methods that are being developed. And decommissioning. During the commissioning, the turbine and generating housing will most likely be removed from the spar hole by reversing the installation procedure and brought back to shore for recycling. Regarding the spar, we are looking into different options in order to being able to either reverse the installation procedure or decommission this spar hole in a cost-efficient and efficient manner. This is still under development. My last slide is, I will mention here that the concession application has been written in collaboration with the Met Center in Norway. This is the permission for the site. All stakeholders have been verbally already approved, and we are very positive to SeaTwirl for the chosen site. We are happy to work with Met Center and have great faith in them, and they have good references from other similar projects as well. And I also put up Haugaland Kraft here as well, because we have a signed power agreement with them, so they will buy the electricity that we're producing from the wind turbine, which is very, very good, I think. And then I also incorporated Unitech here as well, because they are also a local company close to the site, and Unitech will provide the export cable for S2. So we have a good network in Norway, and we are speaking to all the partners. So summing up, we think we are that our SeaTwirl technology is a game changer in offshore wind. And now we are taking on more questions.
Okay, thank you so much, Jonas, and thank you for all the questions. As we mentioned, we have more than 100 questions, and we're trying to take them as they come in, and I will do answer some questions after my presentation, and then Jonas will come back and answer some more technical questions in the end as well. So thank you very much. If we look ahead, then obviously our main challenge and focus is the installation of the S2. We have the installation date is the summer of 2022, and to get there in time and to make sure everything works, we are most important is the team that we have within SeaTwirl, that we have the right skills and the right motivation, so we are very confident about that. We also work with really good subcontractors, which is very important, and also making sure that we have good access to good support, that we have access to the S2, which is great that we are installing not too far away from our office. And also in Norway we have good access to experts and subcontractors that really knows the offshore business. And as you see also, we do a lot of analysis, we do a lot of calculations and simulations to make sure that we are in line. And then also, as I mentioned before, we really work with good subcontractors for the different parts of the unit. And it's very exciting that many of our subcontractors are also really eager to work with us and do a great project. When it comes to financing and the commercialization of the company, it is still a few years ahead. We will for some time continue to rely upon external capitals from shareholders, third parties, and also grants or soft funding. We are currently in the middle of a rights issue, and we are incredibly proud and grateful that our main owner and also everybody in the board has clearly shown us that they want to take part of this journey and they are standing behind the company. So that makes us very happy and grateful. When it comes to grant strategy, I just want to mention that for us, it's very important to work with the grants that are in line with our roadmap, where we are aiming, what we want to do. So we have to be clever and apply and work with the right grants for the company. So we are doing that together with the experts in the subject. So we will hopefully continue having good chances of soft funding. If we look at the opportunities, when we during the summer and spring, we have worked really hard on our business plan. And we ended up kind of dividing our opportunities into two different segments. We had one local solutions we call, or local grid, that within the S2 that we are now building, it's primarily niche markets like islands, remote areas. It could be industrial applications like fish farms. And it's also processes in the offshore oil and gas production. And we have a lot of good conversations with different applications and companies around the world. And so we're getting good feedback when it comes to the future development of the S2 application, which I will mention a little bit later on. The other segment that obviously we talk about and we mentioned before is the wind farm. The wind farms, to be suitable for the wind farms, we have to have a larger size of the turbine than the S2. The generation after S2 is estimated to have an output between 3 and 8 megawatts. And this is obviously a lot of work where we take input from the different projects that are going, the different sites and our potential partners and customers. And after the SX, we are obviously looking at turbines larger than 3 to 8 megawatt. Andreas mentioned before that studies has shown that the vertical have the opportunity to grow up to 30 megawatts. And obviously you become a bit humble when you look at the size and the scope of work, but we take it step by step. If we could dream, and I think dreaming is very important for a company that like ourselves. We are in the middle of the development. When we started doing the business plan and we were going into the phase where we actually gonna build the S2, and one of the questions was related to the timeline of the S2. And obviously we are designing something that nobody has designed before, which means that you will always stumble upon something that make or might make your timeline stretch a little bit. It's also very digital because you can only install and work in the ocean a specific time of the year. So if you don't hit 2020, then suddenly you hit 2021. So you don't want to be there in the middle of the winter. But it's also for respect for the shareholders and the main owner when we are doing the business plan to deliver something professional when it comes to the design of the unit, that we have done all and everything we can when it comes to calculations and analysis and simulations. But also the business plan needs to contain what could be the customers, what could be the potential markets, what are the future units, when are you becoming commercial, which are the homework that we have been doing for quite some time now. And in the short term, if we look at the scenario that we looked in the business plan, in the short term, we obviously want to develop the S2 and continue with that development because we see a lot of promising applications and business opportunities for the S2. And we want to work to achieve a lower capex and obviously a lower LCOE for that unit. And in the local grid segment, we also have a lot of different requests for a smaller unit. And in this picture, we actually call it S0. And now we are talking about something 100 to 300 kilowatts. And that could be a very interesting application for the local segment. If we then jump into the wind farm that I just spoke about before, then obviously we need to grow up larger units, and then the SX is very exciting. And as I mentioned, 3 to 8 megawatts, we need to come back to that because there's a lot of input and also lessons learned from the S2 applications that will affect where we go from there. And I think I just hope that you got. We will continue asking questions. I have some questions I think that's been sent in commercially, and I will start with those. And I hope that you got to get to know us a little bit more as a company. I hope that we have been able to convey the energy and the excitement that we feel about what we are doing in SeaTwirl. We are listed, which means that it's always very difficult to know what you can say and not say. We want to say a lot because we are happy about what we are doing. So hopefully you can continue joining us. The intention is to have more information coming out continuously, and we will also continue with this type of forum during next year in one way or another. But let us come back with that. All right, I will look into some of the questions.
It doesn't stop here, of course, but I think for today.
Yeah, and and we're not going to recycle us in the team since we are
Reuse.
We are here to stay. Reuse. Yeah. First of all, I think we want to thank the whole team for helping us performing this day. We also want to thank all of you guys that's been fighting on with us throughout 3.5 hours. All the good questions. We're really happy that we finally got to do this technical day. We wanted to have you in the room. We hope we can do something in the future where we have more interaction and we can show you more of the things that we actually are producing. But I think the timing could actually be good since now we are going into that phase for the S2. Yeah. So thank you again and have a good lunch and see you soon.
Thank you very much. It's been a pleasure.